Hello everyone, and welcome back to another Strategoy video. After taking an unexpectedly long break from the series as initially planned, Ryan here with a solo MathHammer installment. This time we'll be exploring the probabilistic element that's most crucial to our beloved game of Warhammer, that of the D6 roll. In the mini-series to follow, we'll tackle the ins and outs of everything you ever wanted to know about a D6, from the basics to rerolls and everything in between. But before I get ahead of myself, if you want to keep in touch, join our Strategoy Discord, where Jonas himself and I will be happy to chat with you there. And please do subscribe if you want to stay up to date. In this video, we'll be laying the groundwork for all of our upcoming probabilistic talk, which of course also applies to the D6 in particular. We'll begin by getting the elephant in the room out of the way by discussing our golden assumption, before moving on to fleshing out the ideas of the uniform distribution and measures of central tendency like the mean, median, and mode, and how all these concepts apply to a D6 roll in particular. And of course, we'll conclude with some highlights of what's to come in the remainder of this series. Though we can dive into the wonderful world of the D6 in all its glory, I would be remiss not to acknowledge the elephant in the room when discussing any dice rolls. So let's get that out of the way for thoroughness' sake. When we compute any of the probabilities we're going to see in the rest of the channel's MathHammer computations, we're assuming the D6 rolls are fair. In layman's terms, this means that the D6 is not weighted more on any one side than any of the other 5, essentially giving us a perfectly even chance of getting each of the 6 values. In such a case, we call this a uniform distribution, and this helps us simplify the probabilistic outcomes we're going to compute. But in reality, no one side is actually 100% perfectly evenly weighted with any other. Hell, even the fairness of computer-generated random number generation can technically be called into question. But the important thing here is that all 6 sides are close enough to one another to functionally being the same. For example, if each side is off by a margin of error of, let's say, 0.1%, then all of our computations will still hold up. Furthermore, we might want to go ahead and acknowledge that it's technically possible for a player to get good at rolling the numbers they want on their dice, but short of making them always roll a bunch of dice at once and then somehow randomly selecting from that group, we're ultimately just going to have to remember the following. That this is just a game, and anyone antisocial enough to really try to cheat that way isn't really worth playing against anyway, right? Or perhaps even having in your life at all. From now on, let's assume all of our dice throws are fair, or fair enough not to make a notable difference, and let's get on with the math hammering. So as I mentioned before, a D6 roll follows what we in the probability world call a uniform distribution. But let's spell this out a little more clearly. The term distribution is merely a fancy way of saying the spread of likelihoods or probabilities amongst all possible rolls we could make. So, as you see on the screen here, if a die is fair, what is the chance we roll a 1? Well, there are 6 possible outcomes on the die, so that would be a 1 out of 6 chance. And what's the chance we roll a 2, or a 3, or any other value for that matter? Also, a 1 out of 6. Therefore, since the chance of rolling any single value is the same, we say that the distribution is uniform. Here we have a bar chart visualization of that concept. Along the horizontal axis, we see 6 locations, 1 for each potential dice roll. And the bar for that given value is only as high as the chance that it could occur. So in this case, 16.67%, or 1/6. Notably, all 6 die rolls columns are exactly the same height, or put another way, the path from left to right here is flat. Well, ignoring the gaps between the columns, but we could have visualized it another way if we want to get that picky, right? For those out there in Strategoy land wanting to take this one step further into statistics lingo, we call this concept the probability mass function of our distribution, but that little piece of information definitely won't be on the test. That said, I do keep reusing that terminology just to be clear that we're still talking about the same kind of thing. And to be fair, a lot of times we call it the PMF, which is what you're going to hear more often in statistics talk. Now, normally the next step in visualizing a distribution would be to systematically work out our way from left to right in this chart, progressively adding up all of the probabilities that led up to the one at hand until we get to 100% probability. Let's take a look at how this would play out. First, let's start with the chance that we roll a 1, or 1 over 6. So again, 16.67%. Nothing new here since that's the starting point for this exercise. We move on to the second slot. We're now interested in the chance that we roll either a 2 or all previous values, which would include a 1. So let's take the 1/6 height of the previous column and add it to our current one, like we see on the screen here. So in effect, it's twice as likely, from 1/6 to 1/3, or 16.67% to 33.33%. Then we move on to the third column, and when we do that, we're simply adding yet again everything that came before it. And we continue this process up until the sixth column, where we finally got 100% of our probabilities. So here's 4, here's 5, and here's 6. While this process, which we call a cumulative distribution function, might be intuitive, something in the MathHammer part of your brain might be telling you that something here feels off, even if you can't quite put your finger on it. Well, let's examine what this process would mean in the real world of Warhammer. While rolling a 1 does work out to a 1 out of 6 chance, we don't often actually think of the game in terms of rolling say a 2 or less, the equivalent of the second column. Rather, we normally think of the chance of rolling a certain value or higher, right? As a side note, one notable exception here would be battle shock tests, where we generally want to roll low, but I'll be saving that for a dedicated video later on. So back to the topic at hand. This is where the concept of a reversed CDF, or cumulative distribution function, would come in. And I'm going to clear the slide so that we can start the process over. Essentially, what we do here is the same as what we did before with the regular cumulative distribution, but instead of going from left to right, we're going to reverse it and go from right to left. So we start with the chance of rolling a 6, which, like any other value, is still a 1 over 6. And then as we make our way left to the 5 column, we add that 1 over 6 to the 1 over 6 currently in the 5 column to get a total of 2 over 6. Then we can repeat this for the 4 column by moving one step leftwards, giving us 3 over 6. If this is looking familiar, that's because all we're doing here is just computing the chances for a 6 plus, a 5 plus, or a 4 plus, respectively. To save a little time, I'll go ahead and complete the rest of the chart here. While this is perhaps too dumbed down of an example for some of you out there, we're really just using the basic D6 roll to establish how this visual tool will come in handy once we start exploring way more complex probability distributions, most notably the binomial distribution, but again, this terminology won't be on the exam. Alright, to round out this video's theoretical concepts, I want to briefly talk about averages. Now, for those of you who are in the know, you're well aware that the word average is often called the mean in mathematical speak, but this is a bit of an oversimplification, as we in everyday language often use the word average, quote unquote, to mean one of 3 mathematical concepts: the mean, the median, and the mode. So the mean, or the most commonly associated mathematical term with the word average, is computed by summing up all values and dividing by the number of sources for those values we summed up. In some situations, this is more intuitive than in others, though. For example, if we take the average of 2, 4, and 6, so 2 plus 4 plus 6 equals 12, divided by the number of terms, so 3, we get 4. This is pretty intuitive, as it's not only easy to compute, but our answer is actually one of our 3 values, the 4 itself. But what if we take the average of 2 and 4? Well, that's 2 plus 4 equals 6 divided by 2, giving us 3. Okay, so no longer one of our 2 values, but still intuitive enough, as it's the obvious halfway point between 2 and 4, right? Well, let's take it one step further and take the average of 3 and 4. So that would be 3 plus 4 equals 7 divided by 2, giving us a 3.5. Well, if we were just talking about dice rolls, how on earth would we make sense of an average of 3.5? This isn't even a value one can roll, as all values on a die are whole numbers, right? Well, as we discussed in a previous video where we introduced the concept of expected value, the number we get out of our calculations might not end up being all that intuitive, but it's way more precise than simply saying the average is a 3 or a 4. And this is where the concept of a median is going to come into play. The median is simply the most centrally located value amongst all values that we're computing, but importantly, this has to be evaluated after sorting them from lowest to highest. When we computed the mean, the order didn't matter though. So back when we used 2, 4, and 6 as an example, it's easy to see that the middlemost value is a 4, right? So here on the screen we see that we need to sort them, and then we see I've highlighted that the 4, which is now in the middle, is the median. And thus we weren't surprised when our average ended up being the middle one. Well, this is largely due to the fact that in everyday speech, when we say average, what we're really saying is the median. Take for example the population of all English-speaking people on the planet. What do you think the average income is? Most likely your answer will actually be quite different than the true average or mean, as extremely rich outliers like Jeff Bezos, Elon Musk, and Bill Gates will end up pulling the actual average up way too high. But if we instead took the median, as in the incomes in the middle after sorting all incomes from lowest to highest, you probably would get much closer to your guess. The point here is that when some people think about the average dice roll on a single d6, they don't like saying 3.5 because that's simultaneously kind of abstract and not even a potential result. So that they will instead often round to either side of it and say it's either a 3 or a 4. Technically speaking, the median here is still the mean of those two numbers, so again a 3.5. But when we have two values like this for the median, I like to still refer to the two values as a range for maximum clarity. So here we've got this in slide form here. If we take the median of a d6, so of course the results would be 1, 2, 3, 4, 5, and 6, and we've already sorted them. And then you can see that because it's an even number of potential values, we actually have two that are most centrally located. That would be the 3 and a 4, so in a range from 3 to 4. But technically, you can take the mean of those numbers to get 7 divided by 2 as 3.5, which is easy enough to compute or to see just by saying it's 3 or 4, especially when they're right next to each other like that. All right, but if you really think about it, a 3 or a 4 is no more common a dice roll than a 1 or a 2, or a 5 and a 6, or even a 2 and a 6, two numbers that aren't right next to each other. After all dice rolls are equally likely, right? And this brings us to the concept of the mode, or the single most frequent value amongst all possible values. And seeing as none of our 6 die rolls is actually more common than the others, we could either say that all values are the mode, or none of them. So in everyday speech, someone thinking of the mode as the average is actually just answering the question, of all possible values I might see, which one am I most likely to see? It could actually be that the most likely single value is super low or super high, but both the average and or median could be much more centrally located. In fact, it's entirely possible that none of the three are all that near each other. Take the following collection of numbers: 1, 1, 22, 24, and 1002. In this scenario, what is the mean? Well, we sum them all up for a total of 1050 and divide by the number of items we summed, so 5, giving us 210. Alright, well, what's the median? Well, since we've already sorted them from lowest to highest, and there are an odd number of items, we can simply pick the middle option, which gives us 22. So the median is 22. And lastly, what's the mode? Well, it's the single most common value of our 5 values. And since the only number we have more than once is a 1, well, that's our mode. As you can see here, 1 occurs 2 times and everything else occurs only 1 time. So the mode is a 1. So as you can see, our 3 measures of central tendency are quite different indeed, as we have one measure of central tendency at 210, one at 22, and one at 1. Fortunately, in MathHammer land, these discrepancies are often relatively rare, and we can just focus on the mean or expected value. As we saw in the Intro to MathHammer video, which we'll try to link here, when discussing a 2d3 roll, due to the nature of adding two dice rolls that each follow a uniform distribution, hence a d3 plus another d3, the resulting distribution of sums actually has a much different distribution of its own. To save time explaining, I'll go ahead and just pop the graph up on the screen now. As you can see, we have a symmetrical distribution of 5 potential values where the middlemost value of 4 is the most common, occurring 3 out of 9 times, or 1/3 of the time when simplified, so 33.33%. So putting our terminology from above to the test, let's see if we can figure out what the mean, median, and mode of this result would be. Let's start with the mode, as that's the easiest to just see from inspecting the graph. All we need to do is find the tallest single bar for a given number, and that's our mode. Thus, the 4 is the single most likely result to get from a 2d3 roll, right? Well, how about the median? Seeing as we already have our terms sorted from lowest to highest, all we actually have to do is find the middlemost term, which happens to be a 4 again. This was especially easy since we had an odd number of possible results, which only gives us one clear candidate for the middle term. And finally, though you might already be fully convinced that the mean is in fact also a 4, and you would be correct, the only foolproof way to confirm this is to do the math yourself. So let's do that now. Alright, this involves first computing all of the chances that a given score from 2 to 6 will occur, as seen in the sequence of charts here, and then taking the probability of any given result, say a 1 over 9 for a 2 on 2d3, and multiplying it by the result itself, so a 2. Then we'll repeat for all other results until you've covered all possibilities. So just to quickly walk you through the chart, we've seen this in the Intro to MathHammer video, but the upper left-hand one is showing you what possible combos you could get on two d3 rolls, so a value of 1 and 1, 1 and 2, 1 and 3, 2 and 1, 2 and 2, 2 and 3, and so forth. And then I summed those up, and you can see that the chance that you get a sum of 2 only happens 1 out of these 9 choices, and same with 6, but the 4 happens 3 out of the 9 choices, which is what the bottom table functionally is, right? So leaving the final computation from the last slide as a point of reference at the bottom of the screen, this gives us the following. If we multiply 2, so the chance that we get 2 times its chance itself, so 1 over 9, we get 2 over 9. Or then the value of 3 times the chance we get a value of 3, which is 2 over 9, equals 6 over 9, and so forth. 4 times 3 over 9 gives us 12 over 9, 5 times 2 over 9 is 10 over 9, and 6 times 1 over 9 is 6 over 9. So then we're going to sum all these together to get 36 over 9, or, when simplified, just simply 4. So yes, we have in fact confirmed that the mean as well as the median of a 2d3 roll and mode all come out to 4. Not only does this give us a practical example using these 3 terms, but it also clearly illustrates why it's so easy for people to mix and match the 3 concepts in everyday speech, given that with something like this, the results often come out to exactly the same thing. And just to be super clear with our D6 roll, not the 2D3, the mean was again 3.5. The median is also technically a 3.5, but more intuitively is better represented as a range from 3 to 4. And the mode is either all 6 values or none, depending on how you look at it. Alright, for those of you that are curious, I've gone ahead and included graphs here showing the difference between the probability mass functions, so the chance you get a specific result on a die roll, between a D6 and 2D3, which is shown in the graph on the left, as well as the corresponding reverse cumulative distribution functions. So again, that would be the chance that you get a certain value or higher, like a 1 plus, 3 plus, 5 plus, shown in the graph on the right. So obviously the D6s are in blue and the 2D3 results are in orange. While the PMF, or probability mass function, seen on the left, might be interesting in theory, in the game itself we usually find the CDF, or cumulative distribution function, more interesting, so the graph on the right. And there you can see that the 2D3 performs as well or better than the D6 up until the 5 plus threshold. So it's matching it. The 2D3 is doing better up to that point, But for a 6 plus, the D6 just narrowly outperforms 2D3. So in practical terms, let's say you had two identical spells that each did either D6 or 2D3 mortal wounds, and you needed your spell to do at least 3 wounds on the target. So you know what you need before you start rolling. In that case, while this is 67% likely on a D6, so 2/3, it's all the way up at 89% likelihood for 2D3. So that would be the better choice. But let's say you needed to do exactly 6 mortal wounds. Well, in that case, though the D6's 17% chance of performing that well is pretty low, so getting a 6, it's still higher than the 2D3's 11% chance. As such, it's computations like these that better let us evaluate strategic outcomes, not only for in-play decision making, but also for list building and army choices. And there we have it. But this first video on D6 rolls far from covers the whole range of things we need to discuss, so hopefully it has whet your appetite for more to come, meanwhile setting the stage for some of the concepts and terminology we'll be throwing out there regularly in those discussions. In the follow-up video, or videos if necessary, we'll flesh out all kinds of re-rolls, both ones and failed rolls in general, plus or minus 1 to those die rolls, and the effect of exploding 6s, so there's plenty out there to look forward to. And as much as this video here has been a little bit covering your basic math and probabilistic stuff that you might remember from school, I really do think it's a good starting point as a reference for those that need to brush up on that, but also to see how it's applied to the D6s. And like I said at the intro, we're going to see it come up again with all kinds of different probability things. So good to just get it out of the way. In the meantime, please feel free to like, subscribe, and comment below, as well as joining Jonas and myself over in our Discord channel and in the comments, which I'm more active in myself. We've got tons of more content yet to come and are super psyched at how much growth we've been seeing in our little community lately. So until next time, Ryan out.